Welcome, everyone, to today's Explainer. Let's jump right into a rigorous examination of the Allais effect. Now, we aren't going to rely on standard Newtonian approximations today. Instead, we are analyzing this fascinating phenomenon through the precise theoretical lens of topological geometrodynamics, or TGD, as developed by Dr. Matti Pitkänen. We're going to elevate our discourse to examine fundamental space-time warping and its macroscopic quantum implications. Let's get started. We absolutely must anchor our discourse on this critical empirical anomaly. The figure you see here, roughly 5 times 10 to the negative 4, is certainly not a mere rounding error. It represents a macroscopic frequency reduction. Specifically, it's a massive fractional drop in the oscillation frequency of a paraconical pendulum observed right in the middle of a solar eclipse. A fractional change of this magnitude is exponentially larger than anything classical gravitational screening models would ever permit. So we have to ask ourselves, what fundamental geometric mechanism is actually responsible for this?
Our syllabus for today is structured as follows. First, the Allais pendulum anomaly. Second, space-time warping, specifically contrasting TGD with general relativity. Third, Hamilton-Jacobi structure modifications. Fourth, the frequency reduction mechanism. And finally, the implications for quantum ontology.
Let's move directly into Section 1, the Allais pendulum anomaly.
If we trace the chronology of these observations, it reveals a highly dynamic, undeniably anomalous phenomenon. Back in 1954, Maurice Allais noted a sudden, jarring 13.5-degree shift in the azimuth of a paracanonical pendulum's oscillation plane during an eclipse. Then, moving to 1961, Jeverdon and his colleagues recorded that macroscopic frequency reduction we noted just a moment ago. Later, in 2006 and 2009, Olenici and others observed correlated anomalies across widely separated geographic locations. These phenomena strictly, and I mean strictly, defy classical gravitational or general relativistic screening predictions.
To summarize these characteristics, we are observing extreme transversal forces, a drastic drop in frequency, and dynamic occurrences not just during but adjacent to solar eclipses. Furthermore, this non-local correlation across vast geographic distances strongly indicates a continuous anisotropy of space itself. These precise data points demand a paradigm shift. We are observing effects that move far, far beyond the limitations of mere geometric optics or classical shadowing. Which brings us to Section 2, space-time warping. Comparing TGD directly with general relativity. Here is where we reach a profound ontological divergence, specifically regarding the fundamental nature of spacetime. In standard general relativity, vacuum solutions simply cannot warp. The metric tensor is rigidly constrained by Einstein's field equations. The vacuum is assumed to be flat or maximally symmetric. However, TGD inherently permits warped minimal surfaces. Because spacetime in TGD is formulated as a 4-dimensional surface embedded in an 8-dimensional space, these minimal surface solutions can warp without generating a traditional classical force field. Think of it as conceptually analogous to a geometrically critical, vibrating metal plate. This warping is a dynamic property of the vacuum itself, representing the core difference between TGD and GR. If you examine the induced metric mathematically, it remains formally flat, yet it features a crucial deformation of the Poincare group acting as isometries. This formulation allows the vacuum to warp, fundamentally altering the topological landscape without invoking standard mass-energy-driven gravitation. This specific capacity for space-time to warp at moments of quantum criticality is exactly what allows TGD to explain macroscopic anomalies where general relativity remains entirely silent. Moving to Section 3, Hamilton-Jacobi structure modifications. To accurately model a system experiencing this warping, we introduce the gravitational Planck constant, denoted as h sub gr. This is a vital conceptual leap. We are no longer modeling our pendulum as a classical metallic bob swinging on a wire. We are treating it as a macroscopic quantum harmonic oscillator. This parameter characterizes large-scale quantum coherence, effectively substituting the standard Planck constant, where beta 0 represents a specific fundamental velocity parameter of the given system. Consequently, because the space-time surface itself is warped, any path traversing it is effectively elongated. This establishes the highly significant concept of a reduced effective light velocity, which we denote as c-sharp. As the vacuum warps, the effective speed at which light, or indeed any interaction, propagates along that specific topological surface noticeably decreases. This geometric elongation is directly derived from the induced metric we examined a moment ago. At moments of macroscopic quantum criticality, such as the precise gravitational alignment of the Earth, Moon, and Sun during an eclipse, we see holomorphic transformations occur. The complex coordinates undergo a time-dependent U1 rotation. Essentially, this is a continuous phase shift, which induces a literal physical twist in the local space-time embedding. We refer to these as twisted Hamilton-Jacobi structures. The monopole flux tubes mediating the gravitational interaction are geometrically twisted by this rare celestial alignment.
Let's now synthesize this in Section 4, the frequency reduction mechanism.
Let's trace the precise mechanism for this proposed frequency reduction step by step. Step 1. The celestial alignment creates quantum criticality, which triggers the space-time warping unique to the TGD framework. Step 2. This warping twists the Hamilton-Jacobi structure of the gravitational field body. Step 3. Because of this twisted, elongated path, the effective light velocity, c#, is severely reduced. And finally, step 4. Governed by macroscopic quantum relationships, the pendulum's oscillation frequency drops proportionally to match that reduced velocity parameter.
Consider the quantitative precision here regarding the beta-zero parameter. The value for the Sun and inner planets sits precisely at roughly 2 to the power of -11. What is conceptually fascinating about this is that the required reduction of the velocity parameter to account for the Allais anomaly perfectly matches this observed frequency fraction. It aligns exactly with the orbital velocities of our local solar system relative to the galactic center.
The mathematical synthesis of this mechanism rests entirely upon the energy equation. Energy equals h_g times frequency. For a quantum harmonic oscillator, this relation is non-negotiable. If our effective light velocity, c#, replaces beta-zero in the Planck's constant denominator and is reduced by a factor of 2 to the -11 due to critical warping, the oscillator frequency must experience an identical, massive proportional drop simply to maintain the quantum state. This specific geometric mechanism perfectly accounts for the magnitude of the anomalous frequency reduction.
This leads us to our final section, implications for quantum ontology. The implications here are quite frankly staggering. The Allais effect transcends classical gravimetry. It provides empirical validation for macroscopic quantum mechanics governed by a large gravitational Planck constant. It strongly suggests gravitation isn't merely curved empty space, but is mediated by monopole flux tubes acting similarly to incompressible hydrodynamic flows. Furthermore, the non-local nature of the eclipse shadow implicates quantum diffraction not in standard space, but within the geometric framework known as the world of classical worlds. Ultimately, this firmly supports zero energy ontology.
As Dr. Pitkin himself articulates so well, we are not merely tweaking Newtonian mechanics here. We are observing a profound manifestation of fundamental quantum topology. The Allais effect is an empirical window into a reality governed by a hierarchy of Planck constants and zero energy ontology. It forces us as physicists to logically abandon the classical assumption of a rigid, unyielding vacuum space.
I leave you, the rigorous learner, to ponder this final implication. If localized quantum criticality and space-time warping can so drastically modify macroscopic frequencies in a simple laboratory pendulum, to what extent is our local universe continuously modulating its effective light velocity? Are we, and the massive celestial systems around us, constantly operating under fluctuating, reduced light velocities at the whim of quantum critical space-time warping? I leave you to consider those implications. Thank you for joining me for this explainer.